If you want to take the absolute shortest, fastest route from New York to Tokyo.
Right, which is a massive distance.
Exactly. And, pulling out a standard map of the world and just drawing a straight line between those two cities is, well, it's just about the worst thing you can do.
It really is, yeah.
But it feels completely counterintuitive, right? Like, since we were kids, we've been taught that the shortest distance between 2 points is a straight line.
You just grab a ruler and go.
Right. You find point A, you find point B, you put a ruler down on the paper, and you draw a line. Your brain automatically tells you that you've just found the most efficient path.
It's hardwired into us.
It is. But today, we are going to uncover why the maps you've trusted your entire life are, mathematically speaking, actively lying to you.
I mean, we are so conditioned by two-dimensional representations of the world that we completely lose sight of the three-dimensional reality we actually live on.
Yeah.
When you take a giant sphere and force it to sit flat on a desk or, a screen, you create a massive cartographic deception.
A deception. I love that word for this.
Well, it's true. The straight lines we intuitively trust are warped, and the actual shortest paths look completely absurd to our human eyes.
Welcome to today's deep dive, everyone. Our mission today is to break down this navigational deception.
We've got some great stuff to cover.
We really do. We are going to figure out why straight lines on maps are tricking our brains, and how traveling across a 3D sphere gets completely and ridiculously distorted when we try to flatten it onto a 2D grid.
Right.
And we've got an incredible set of materials for you today. We are pulling heavily from a brilliant article titled Navigating the Sphere, From Small Circles to Great Circles.
That's a fantastic piece.
It really is. And we'll also be walking through a highly detailed mathematical diagram that accompanies it, which breaks down arc length ratios on a globe.
Taking a look at these sources, it fundamentally changes how you perceive global travel. I mean, they take something you probably take for granted, how an airplane gets from one continent to another, and force you to look at the literal physical geometry driving that journey.
But, before we can even touch the paper maps or look at the math, we really have to rebuild our mental model of the Earth itself.
Absolutely. We have to start with the physical shape.
Right, the globe. If you are standing on a sphere and you want to draw a path around it, you basically have two options.
This too, yeah.
And understanding the difference between those two options is really the foundation of this entire deep dive.
To understand navigation, you have to understand the physical difference between a great circle and a small circle.
Right.
Let's imagine a perfectly spherical planet, just suspended in space. If you want to draw a continuous circle around the outside of that planet, the way you slice through that sphere determines, well, everything about the distance you'll travel.
Okay, let's unpack this for you listening at home.
I like a good visual.
Yeah, picture this. Imagine you are holding a perfectly round orange in your hand.
Okay, I've got my orange.
And you have a kitchen knife. If you want to slice that orange so that you create the widest possible circle around the outside skin, you have to cut dead center.
Exactly, dead center.
Your knife has to pass straight through the absolute core of the fruit.
And cartographers and mathematicians, they call that a great circle.
A great circle.
Yeah. A great circle is any circle drawn on the surface of a sphere where the center of that circle perfectly coincides with the center of the sphere itself.
So the middle of the circle is the middle of the Earth.
Right. If your imaginary knife passes through the dead center core of the Earth, the line it leaves on the surface is a great circle.
The most famous one being the equator, obviously.
Yes, the classic example.
It perfectly splits the planet into the northern and southern hemispheres, and our sources give us the baseline math for this.
They do.
If you travel exactly halfway around the equator, let's say you start at 0 degrees longitude and travel all the way to 180 degrees longitude, the distance of that path is the radius of the Earth, which we call r, multiplied by pi.
Right, so r times pi. But, the equator is the primary horizontal baseline. But it is definitely not the only great circle.
Oh, right, the vertical ones.
Exactly. Meridians. The lines of longitude running vertically from the North Pole down to the South Pole, they function the exact same way.
Oh, I see.
Yeah, if you take the prime meridian running through Greenwich, London, and you pair it with its exact opposite on the other side of the planet, the 180-degree meridian, they link up.
They make a full hoop.
Exactly. They form a complete unbroken ring around the Earth.
Yeah.
And because that vertical ring passes perfectly through the North and South poles, its center is, again, the center of the Earth.
But still a great circle.
Yes, it is.
And the reason this matters for our deep dive, the whole reason we care about slicing through the core of the orange, is that an arc along a great circle represents the absolute shortest distance between any 2 points on a sphere.
The absolute shortest.
Right. In geometry, these paths are called geodesics.
Geodesics, yeah.
If you want to travel efficiently, whether you are flying a plane or sailing a ship, you desperately want to be on a great circle path.
Which naturally brings us to the alternative, which is the small circle.
The small circle.
Right. If a great circle requires your knife to pass through the dead center of the orange, a small circle happens when you cut anywhere else.
Literally anywhere else.
Right. If you slice just the top off the orange or, cut a slice near the bottom, your knife is moving through a plane that is entirely above or below the center.
So the resulting circle on the skin of the fruit is just physically smaller.
Exactly.
And in geographical terms, these are our lines of latitude, the parallels.
Yes. Every single line of latitude in the northern and southern hemispheres, aside from the equator, is a small circle.
Right, because the equator is the great circle.
Exactly. The rest are just parallel rings around the Earth. And as you move further north or south toward the poles, those rings just keep shrinking.
They get tighter and tighter.
Right. If you are standing on a line of latitude, you are standing on a ring whose center is not the center of the Earth. It's just an arbitrary point hovering somewhere along the Earth's axis.
Which introduces a really weird physical constraint for anyone trying to travel.
It does.
Like if you are steering a ship and you want to stay perfectly on a line of latitude, a small circle, you are actually constantly steering your ship to manage the curve.
Yes.
You aren't just going straight in a three-dimensional sense.
No, you're constantly leaning into a turn.
Wow.
To stay parallel to the equator on a spherical surface, you have to continually adjust your heading to sweep around the curvature of the Earth's natural bulge.
That is so wild to think about.
You are actively avoiding the natural straight-ahead path over the curve of the planet to force yourself along that smaller ring.
Okay, we have the physical picture locked in. Slicing through the core gets you a great circle. Slicing off the top gets you a small circle.
Right.
But to really understand why maps deceive us, we have to translate those physical shapes into the math of the path.
The math is where the truth is.
Exactly. Our sources dive deeply into the formulas used to calculate these arc lengths, and we really need to walk through them.
Yeah, let's do it.
But math on audio can be tricky, so we are going to build this picture slowly for you.
Okay, let's imagine you are plotting a trip between two cities.
Okay.
Let's say Madrid and New York.
Classic route.
They sit at roughly the same latitude, roughly 40 degrees north.
Okay, so they are sitting on the same small circle.
Exactly. If we want to calculate the distance of just sailing straight across that line of latitude, we need three distinct variables. First is r, the radius of the Earth itself.
Got it. R is the Earth's radius.
Second, we need the horizontal distance between the cities, the central longitudinal angle. We'll call that angle phi.
So phi is just the size of the horizontal pie slice we are traveling across.
Spot on. And third, we need to know how far north of the equator we are. That is our latitude angle, which we will call theta.
Okay.
For our trip, theta is 40 degrees.
Let me make sure I'm tracking. So we have r for the planet's radius, phi for our horizontal travel, and theta for our vertical position.
That's it.
If I'm the captain of this ship and I decide to just lock my steering wheel and travel perfectly along my small circle latitude line, how do I calculate that distance?
Well, because you are high up on the sphere in the northern hemisphere, the radius of your specific latitude ring is much smaller than the radius of the entire planet.
Because we slice the top off the orange.
Exactly. And to find out exactly how much smaller it is, mathematics gives us a tool, the cosine function.
Ah, cosine.
Right. The radius of a small circle at any latitude theta is the Earth's radius r, multiplied by the cosine of theta. So r times the cosine of theta.
And for those of you trying to picture this, cosine isn't just a random button on a calculator.
No, it actually means something physical here.
Right. It is a mathematical way of mapping how much that orange slice shrinks as you move your knife away from the center. At the equator, it's at its maximum. As you move toward the North Pole, the cosine function elegantly tracks the shrinking radius of those rings until you hit 0 at the very top.
So, having found the shrunken radius of our small circle, calculating the total travel distance is pretty straightforward.
Okay.
We take that new, smaller radius r times the cosine of theta and multiply it by the horizontal distance we want to travel, which is phi.
Right.
This gives us our first formula. The small circle arc length equals r times the cosine of theta times phi.
That makes perfect sense. You're just walking along the edge of a smaller slice of orange.
Exactly.
But here's where our source material throws a massive wrench into our intuition.
Oh, yeah?
If you want to take the true shortest path between New York and Madrid, a geodesic Great Circle path, you cannot stay on that latitude line.
You absolutely cannot.
The formula for the Great Circle length changes entirely.
It does.
The article states that for small to moderate latitudes, the central subtended angle factor at the Earth's core adjusts as 1 minus 2 theta. So the Great Circle length formula becomes r times 1 minus 2 theta times phi.
Right.
Wait, hold on. I am hitting a wall with this.
Okay, what's tripping you up?
I need to push back on this 1 minus 2 theta adjustment because it is scrambling my brain.
It's not intuitive, I know.
If I'm just trying to sail horizontally from New York to Madrid, why in the world am I subtracting double my vertical latitude from the equation? Like, why does my vertical position cause the horizontal angle at the center of the Earth to contract?
This raises an important question, actually.
I'm glad it does because I'm lost.
That struggle you are having with the math is the exact friction between our 2D intuition and 3D reality.
Okay.
Let's step away from the numbers for a second and use physical tension.
I like tension.
Imagine stretching a rubber band across a physical globe. You pin one end in New York and you pin the other end in Madrid.
Got it.
If you manually pull that rubber band down so it sits perfectly horizontally along the 40-degree latitude line, you have to hold it there with your fingers.
Because it wants to snap out of place.
Exactly. The moment you let go, the rubber band will naturally slip upward toward the North Pole.
Oh, wow.
It settles into a gentle curve that arches over the northern Atlantic. And it does that because the physics of tension demand the path of least resistance, which is always the shortest physical distance.
So it moves on its own to find the shortcut.
Yes. By slipping higher up onto the narrower part of the dome of the Earth, the rubber band finds a physically shorter route than wrapping around the wider, bulging base of that latitude line.
It is cutting the corner by going over the top of the curve.
Exactly.
Instead of walking all the way around the wide rim of a dome, it just steps up and walks straight over the top.
And that physical slip up the globe is what the 1 minus 2 theta formula is mathematically modeling.
Mind blown.
Right. The angle at the Earth's core essentially pinches or contracts because you are no longer sweeping around the fat part of the sphere.
Right.
You are letting the natural curvature of the Earth guide you over the top. You abandon the small circle entirely and create a temporary great circle that perfectly connects your two cities.
This completely changes the mental image. The math isn't just an abstract penalty, it's the formula for a three-dimensional shortcut.
Precisely.
And our sources take this a step further. They don't just hand us these two formulas and walk away.
No, they want to prove it.
Right. They compare them directly to prove exactly how much more efficient this great circle navigation actually is. They create a ratio to pit the two paths against each other.
And comparing the two reveals the true scale of the illusion.
Let's hear it.
We take the formula for the inefficient small circle distance r times the cosine of theta times phi and place it next to the highly efficient great circle distance r times 1 minus 2 theta times phi.
Okay.
Because the radius of the Earth r and the horizontal travel distance in phi exist on both sides, they cancel each other out entirely.
Be nice. Simplify it.
Exactly. You are left with a distilled, pure mathematical ratio of cosine of theta to 1 minus 2 theta.
Here's where it gets really interesting.
It really does.
That is the golden ratio of navigation, cosine of theta to 1 minus 2 theta.
Yep.
The article runs a fantastic stress test on this ratio starting at the equator. Let's walk through the equator test for you right now because it proves everything we've talked about so far.
It's the perfect test case.
At the equator, your latitude theta is 0. You have 0 vertical height.
And plugging 0 into our ratio yields an immediate result. The cosine of 0 is exactly 1.
Okay.
On the other side of the ratio, 1 minus 2 times 0 is also 1.
Wow.
So the ratio stands at exactly 1 to 1.
This mathematically verifies our physical orange analogy.
It absolutely does.
At the equator, the small circle and the great circle are the exact same path. There is no efficiency to be gained by arching up or down, because the equator already passes through the dead center core of the Earth.
What's fascinating here is that the geometry is perfectly aligned there. But the real revelation happens when you sail away from the equator and start moving towards the poles.
Things break down.
Exactly. Imagine you are traveling up into Canada or northern Russia. As your latitude, your theta increases, both sides of that ratio start to drop.
Because the Earth is getting narrower.
Right. The overall distance between meridians gets smaller no matter which path you take.
Yeah.
But, and this is the crucial mechanism, they do not drop at the same rate.
And this is where the small circle really starts to punish you.
Absolutely. As your latitude increases, the great circle side of the equation, that 1 minus 2 theta shortcut, decreases significantly faster than the small circle side, the cosine of theta part.
Okay, wow.
The mathematical reality of those two specific functions dictates a widening gap in efficiency.
So the higher up you go.
The worse it gets. As you move further north or south, traveling strictly along your line of latitude becomes incredibly wasteful. The great circle path becomes drastically shorter in comparison.
So let's ground this in reality for a second.
Sure.
If you are a pilot flying cargo from Anchorage, Alaska to northern Europe, and you force your plane to fly perfectly straight east along your line of latitude, you are burning a massive amount of excess jet fuel.
A completely unnecessary amount, yes.
The math practically screams at you to point your nose up, fly over the top of the Arctic curve, and come back down on the other side.
It dictates the entire global logistics network.
Really?
Oh, absolutely. If you pull up a flight tracker app right now and look at planes crossing the Pacific or the Atlantic, their paths always look like massive sweeping arcs pointing toward the poles.
I always wondered about that.
Yeah, they are not taking the scenic route. They are rigorously following the 1 minus 2 theta side of the ratio. They are tracing the geodesic.
So if the math is this definitive, and pilots and ship captains have known this for centuries, why is it so incredibly hard for our brains to accept?
Great question.
Why do I still look at a map and think the straight line is faster? That brings us to the final piece of the puzzle from our sources: cartographic deception. The reason our intuition is poisoned is because of the tools we use to look at the world.
We rely almost entirely on two-dimensional grids.
Right.
When cartographers take this beautiful, mathematically complex 3D sphere and project it onto a flat rectangle, like a standard Mercator projection you see in classrooms or on digital map apps, they have to make geometric compromises.
You can't just peel an orange and lay it flat perfectly.
Exactly. To make a curved surface lay flat without tearing, you have to stretch the northern and southern regions horizontally.
You force a round peg into a square hole, and the geography just distorts to fill the corners of the paper.
And to maintain the grid system on that flat paper, cartographers draw the lines of latitude, those inefficient small circles we talked about, as perfectly straight, horizontal lines from left to right.
And there's the trap.
That's the trap.
Because human beings intuitively, deeply believe that a straight line is the shortest distance between 2 points, moving along one of those flat latitude lines looks like the most efficient route.
It looks perfect on paper.
Right. Your brain sees a perfectly straight line connecting 2 cities on the paper, and your instinct says, that is the absolute fastest way to get there.
But the underlying mathematics of the sphere have just proven to us that it's not.
It's a total lie.
The straight line on the flat map represents the small circle. It represents the slower, longer, forced path around the bulge of the Earth.
So what does this all mean?
Well, this is the cartographic deception in full swing.
Yeah.
Flat projections obscure the true geometric efficiency of the world. Because the map has stretched the poles outward, the true great circle routes the actual physical shortest paths that pilots are flying appear incredibly distorted on the paper.
If you take a pen and draw the true mathematically shortest great circle path between New York and Madrid on a flat map, it looks ridiculous.
It really does.
It looks like a long, bizarre detour looping way up into the North Atlantic, brushing past Newfoundland, before finally curving back down towards Spain.
Exactly. To our to-be-trained eyes, the actual shortcut looks like a massive waste of time.
It looks incredibly inefficient on paper, even though in the physical 3D reality of the planet, it is a mathematically perfect straight line.
Which is wild.
The map is actively gaslighting us, convincing us that the scenic route is the shortcut, and the shortcut is a detour.
If we connect this to the bigger picture, relying on these 2D projections actively works against understanding the physical reality of a 3D globe.
You're right.
The old saying goes, the map is not the territory.
I love that.
Gets perfect here. When you try to translate 3 dimensions into 2, something has to be sacrificed. And in global mapping, what gets sacrificed is the truth of distance.
Wow.
The sheer efficiency of the Great Circle is visually hidden from you, simply so the map can sit flat on a table.
It is genuinely wild to realize how much trust we put into a piece of paper that is geometrically incapable of telling us the whole truth.
It makes you question everything, doesn't it?
It really does.
Yeah.
We have covered a massive amount of ground today. Let's do a quick recap for you to ensure this entire journey from the physical orange to the flat map locks in.
Good idea.
So we started by defining the sphere, realizing that slicing dead center gets you a great circle, the true shortest path.
Right.
Slicing the top or bottom gives you a small circle, which forces you to constantly steer around the Earth's curve.
And from there, we dove into the variables and established the golden ratio of navigation.
The math.
Right. Cosine of theta for the small circle path versus the 1 minus 2 theta contraction for the great circle path.
And we ran the equator test and saw that at 0 degrees latitude, the paths are completely identical, a 1-to-1 ratio.
Perfectly matched.
But the moment you move north or south, that 1 minus 2 theta formula proves its worth. The math mandates that the great circle route shrinks much faster than the small circle route.
Which ultimately revealed the great lie of the flat map.
The gaslighting.
Yes. Because 2D maps draw inefficient latitude lines as perfectly straight, our brains are tricked into thinking those slower small circles are the shortcut. Meanwhile, the actual, faster great circles are visually distorted into long, curved arcs.
It is a phenomenal example of how much longer it actually takes to travel along a straight, small circle rather than a beautifully curved great circle.
It forces you to pause and deeply reconsider how we visualize the world around us.
It really does.
And honestly, it leaves me with a lingering thought about how we approach problem solving in our everyday lives.
Oh, I like where this is going.
Well, think about it. If mapping a 3D physical sphere onto a 2D piece of paper completely distorts our understanding of the absolute shortest distance between 2 points,
Yeah.
how often do the other straight lines in our lives deceive us?
Oh, wow.
We constantly take complex, multi-dimensional problems in business, in relationships, in our careers, and force them into simple, flat spreadsheets or binary pros and cons lists.
We flatten them.
Exactly, we flatten them. What if the frames of reference we use every day to solve our problems are actually obscuring a much faster, beautifully curved path? A path that is sitting right in front of us, if only we stopped assuming that a straight line is always the best way forward.
That is a completely brilliant way to look at it. We think we are taking the smartest, most direct route, but we might just be stuck navigating on a flat map of our own making.
Ignoring the three-dimensional reality of the situation.
Ignoring the reality. Thank you so much for joining us on this deep dive today.
It was a pleasure.
We hope you walk away looking at the globe a little differently. Keep questioning those straight lines around you, and the next time you look at a flat map and expect precision.
The next time you expect a clean, straight line to be the indisputable truth.
Just remember, the actual math of the sphere tells a very different story. We will catch you on the next one.